Amazing students and all the lovers of chemistry out there. I'm super excited to be here once again with you guys. I sincerely hope you've been enjoying this series on redox reactions so far. If there's any other topic you'd want me to go in depth on, please do well to let me know in the comment section below, and I'd be more than happy to do justice to that just for you. All right, now we're moving further in this series to the concept of understanding half reactions. Okay, half reactions. Now, what are half reactions basically? A half reaction consists of two words here. If you notice, it consists of the word half and the word reaction. So a half reaction basically is one part of a redox reaction. It shows either the oxidation process or the reduction process on its own. Now, it's just like having maybe an orange. All right, pardon my drawing skills. Okay, maybe having just this is an orange now, and then you divide it into two. So a redox reaction is much like this orange. One part shows oxidation, while the other part shows reduction. I hope you're following. So one half reaction shows the loss of electrons, that is the oxidation part, while the other half rather, shows the gain of electrons, which is reduction. So each half includes the chemical species that are involved and the number of electrons that have been lost or gained. So now let's proceed and see what next lies in store for us. Why are they important, by the way? Half reactions are important because, first of all, they help you to understand. They help you to understand how electrons are transferred, and they help you to balance redox reactions, especially in acidic and basic media. Now, when we begin to balance redox reactions, you'll see cases where we'll be asked to balance it in acidic medium, and you'll see cases where we'll be asked to balance in a basic medium. All right, so this will be very helpful to us. This is why half reactions are very, very important. So now let's get into the concept of knowing how to write half reactions. If you want to know how to write half reactions, you have to know how to separate an entire redox reaction into the two main halves. So now let's do this example. Let's break a redox reaction into two half reactions. Now we have an example here. We have an example here of zinc, right? Zinc reacting with copper, zinc reacting with copper, and then see the steps that we are going to take. First of all, we need to identify oxidation and reduction. How do we do that? The first element we have here is zinc, Zn, and it migrated to produce Zn2 plus. The other elements we have is copper, Cu2 plus, and then it migrated to become Cu. Now the question is, which one was oxidized, or which one experienced oxidation and which one experienced reduction? Step one, let's identify oxidation and reduction. Remember, I said in our previous lesson, if the oxidation number of an element increases, then we say it has been oxidized or it has undergone oxidation. And if the oxidation number reduces, then we say it has undergone reduction. So now in this case, look at this. Here, zinc, the oxidation number here is 0 because it is in its pure form. And in this case, the oxidation number here is plus 2. So my question now is, from 0 to plus 2, does it increase or does it decrease? Now, I'm sure you said something to the effect of saying it increased. And if you said it increased, that is correct. And when the oxidation number increases, we say it has undergone oxidation from 0 to plus 2. That's oxidation. Now, in this case, next case, copper Cu2 plus to Cu. From here, the oxidation number is +2, and here the oxidation number is 0. Now my question is, from +2 rather to 0, does it increase or decrease? Of course, you know that it decreases. Now my question is, when the oxidation number decreases, what happens? It is called reduction. So that's the first step to take. You break a redox reaction into two halves by identifying the oxidation and the reduction parts. So we've done that. Now what is the next step? The next step is to write the half reactions. How do we do that? Let's get right into it. So now, for zinc, we know that zinc, here is the transformation process, Zn2 plus. What this is telling you is that zinc lost 2 electrons to become Zn2 plus. Now, in order to balance this equation, we need to identify or show those 2 electrons that were lost. And that is why we need to write 2A minus. Now, in redox reactions, we identify electrons by writing an E with a minus sign above it, more like a superscript. Are you seeing how everything is playing out now? So zinc undergoes a transformation process from Zn to Zn2 plus, and then plus 2 electrons over here. Now, same thing goes for copper. We see copper undergoing reduction. Remember, zinc has lost 2 electrons. Now, those 2 electrons that zinc lost were now gained by copper. That is why we have copper Cu2 plus combining with the 2 electrons that have been lost by zinc to produce Cu. Are you seeing how everything is playing out? So now, in this case, we have broken down the redox reactions into two. We have the oxidation half, we have the reduction half, and we have identified the movement of electrons. What is the next thing to do now? At this stage now, we're going to make sure that the number of electrons are balanced in both equations, and then we'll combine them together. Now, in this case, we have 2 electrons, and in this case as well, we have 2 electrons. So the number of electrons in both half reactions are equal. So what do? We combine both equations to balance them out. So at this point, these 2 electrons cancel out these other 2 electrons. So what do? We add the 2 half reactions together to come up with one. So let's do that real quickly. We have Zn plus Cu2 plus, that gives us Zn2 plus Cu. So this is our final equation over here. So that's how we do that. That's how we break a redox reaction into two. So now let's move into something else. In order to write and understand half reactions efficiently, there are three things that you need to do. First, you need to identify the half reactions. I've shown you how to do that. And then you need to make sure that the electrons in both half reactions are equal, and then you merge 2 equations together. So let's see if we can tackle one example and then we'll proceed. Now look at this example. In this case, we have ion reacting with chlorine. So we have Fe2 plus reacting with Cl2. So what is the first step to do? Identify the half reactions. So let's go ahead and identify which part is the oxidation half and which part is the reduction half. So we have Fe2 plus being transformed into Fe3 plus. If you watch closely, you see that the oxidation number changes from +2 to +3. Now, if something moves from +2 to +3, does it increase or decrease? Of course, it increases. And when the oxidation number increases, we say that is oxidation that has taken place. So invariably, we can call this the oxidation half. Now, the same thing goes for the other part, Cl2 being transformed to Cl minus. Now, Over here, you can see that the oxidation number of chlorine is 0 because it is in its pure elemental state. And over here, you can see that there is a charge which indicates its oxidation number, and it is -1. And now, how many atoms of chlorine do we have? We have 2. So therefore, it becomes 2 times -1, which gives us -2. So the oxidation number here is -2. If something goes from 0 and it becomes -2, does it increase or decrease? Of course, it decreases. And when it decreases, we say reduction has taken place. So therefore, this is the reduction half. So we've identified the reduction half, and we've identified the oxidation half. Now, the next thing to do is to indicate the flow of electrons. So for oxidation, it loses electrons. So we indicate the loss of electrons by showing the electron that has been lost. In redox reactions, we indicate electrons by writing E minus. So in this case, it was just one electron that was lost. So that's why we have E minus here. Now for chlorine, chlorine gained 2 electrons. So we have Cl2 plus 2E minus, giving us 2Cl minus. So now we've indicated the oxidation half and we've indicated the reduction half. What is the next thing to do? Next thing to do is to make the electrons equal in both. So let's rewrite what we wrote in the last slide. We have Fe2 plus giving us Fe3 plus E minus. And then for chlorine, we have Cl2 plus 2E minus, giving us 2Cl minus. Now, when they say make the electrons equal in both, what they simply want us to do is to make sure that the number of electrons in the oxidation half must be equal to the number of electrons in the reduction half. So over here we have 1 electron, and over here we have 2 electrons. How do we make it equal now? We'll simply do that by saying this place multiplied by 1 and this place multiplied by 2. So if we do that, it gives us 2 Fe2 plus, and then there's an arrow giving us 2 Fe3 plus, and then plus 2E minus. Can you see what we just did? Now, the same thing goes for here. We are multiplying by 1 this time, so it remains Cl2 plus 2E minus, giving us 2Cl minus. Can you see what we just did? So now, what is the next step to take? Next step to take is to merge them together. The next step to take is to merge them together. So if I remember clearly, we have 2Fe2 plus giving us 2Fe3 plus E minus, and then we have Cl2 plus 2E minus, giving us 2Cl minus. Now, how do we merge them together? We merge them together by cancelling out the electrons. So these 2 electrons here on the reactant side cancels out these 2 electrons here on the product side. So let's merge them together. Reactant side goes with reactant side and product side goes with product side. That gives us 2Fe plus Cl2, giving us 2Fe3 plus 2Cl minus. This is our final balanced equation. So this is how to write the oxidation and reduction half of your redox reactions correctly. So now we are ready to go into the concepts of balancing redox reactions in acidic medium and in basic medium. We've been taking all these steps concept after concept. So right before we do that, I want you to try out these exercises for me. You break them into half reactions and comment on them in the comment section below. Up until now, I want to say thank you for staying with me till the end of this video. It's been an honor and privilege taking you through the course of chemistry. Up until next time, my name is David, and all we do here is to take the mystery out of chemistry so chemi can make history. Do well to like this video, subscribe, and turn on the notification bell icon so when more educational videos like this come out, you'll be the first to be notified. Till next time, stay blessed.